Hello and welcome to the Transient multiphase flow modeling in wells with LedaFlow webinar. Thank you for accepting the invitation. My name's Mike Branchflower. I'm the Global Sales Manager for LedaFlow in Kongsberg. You'll have the opportunity to submit questions by typing them into the questions pane of the control panel. Please send them in at any time during the presentation and demonstration, and we'll answer as many as we can after the presentation and demonstration have been completed. Please also note we've included a LedaFlow product sheet to download in the handouts pane near the bottom. I'll now hand over to Wouter Dijkhuizen, who is the LedaFlow product champion.
Yep, thank you, Mike. So just for starting this webinar, I will have a very short introduction as a PowerPoint presentation, just to introduce a couple of things, and then we'll dive straight into the demonstration part. So the things I will explain in terms of relevant functionality are the well builder, the well device, how to model gas lift in different ways in LedaFlow, the initial conditions, and then we get to the demonstration part where we'll simulate a well cleanup case built from scratch. Okay, so the first functionality I would like to introduce is the well builder. So the purpose of it is to simplify defining the walls in the LedaFlow model, and specifically when modeling fluid flow in an annulus. So this is a little bit complicated to do that by defining the walls manually. So that's why we created this well builder, to make it easier to do that based on the completion information. So I'll just demonstrate that afterwards. So it's possible to model different annular spaces in LedaFlow, both the A annulus and the B annulus, depending on what you want to do. The benefits of modeling the annulus in the LedaFlow model are to get a more accurate temperature prediction in the well, both for the production fluids and the lift gas. So obviously there is heat transfer between the lift gas in the A annulus and the production fluids, but also if there's lift gas in the annulus, then there can be radiation heat transfer between the tubing and the casing, and all of those effects are taken into account when you model the annulus in LedaFlow. So that's one benefit. There's also the benefit of having a more accurate and realistic gas lift modeling, and that is because the annulus allows you to use the leak as a gas lift valve, and that makes the gas lift dependent on the casing and tubing pressure, which is more realistic than using a simple source, and we'll come back to that later. Then the well device in LedaFlow, so that is used for modeling the flow between the reservoir and the wellbore, also called inflow performance relationship, or IPR. So the flow rate here depends on the drawdown, meaning the reservoir minus the bottom hole pressure. So it's a pressure dependent flow rate. It is distributed along a user-defined length of the well, so it's possible to have inflow in more than one cell at the bottom of the well. And it handles both production and injection. And it's very common, like we will see in the demonstration, that even for a producing well, there can be temporarily some injection into the reservoir. That's quite normal. And then LedaFlow supports all kinds of different IPR types, like the linear PI, which is the classic version. We also have IPR tables and more complicated correlations like Vogel and back pressure. And in terms of gas lift modeling in LedaFlow, so there are basically two approaches. So the simplest one is using a source, which allows you to define a flow rate that can be constant or it can be time dependent. And this is very useful when determining how much gas lift is required. So you can do a parametric study, for instance, varying the gas flow rate. So it has its purposes. And if you want to model this more in a more reasonable way, more realistic, then it's possible to use a gas lift valve, which is modeled using a leak device. So that takes into account the fact that in reality the flow is pressure driven, And also, if you use gas lift valve tables, it allows you to open and close the gas lift valve automatically based on the casing and tubing pressure, which is what happens in reality. And then finally, if you have these gas lift valve tables active, then the LedaFlow can also adjust for any temperature changes, which can have quite a big effect on the gas lift valves, because there's typically a nitrogen-filled bellows in the gas lift valve, and that one is the pressure there depends on the temperature because it's a closed volume. So it's that has quite a big effect on the operating characteristics of the gas lift valve. So all of that can be taken into account if you model the annulus with a leak as a gas lift valve. And finally, the functionality that we'll use today for starting the dynamic simulation is the initial conditions. So user-defined initial conditions allow you to control over what kind of fluid is where in the pipes. So this is as opposed to a steady state initialization using the steady state preprocessor. The main assumption here is that there's no flow. So the pressure drop that you get from the initialization, it's only hydrostatic. But that is consistent with it's consistent with the LedaFlow model for a startup. So basically, you're starting from no flow, and then the dynamic simulation will start producing or not. So all of the user inputs for initial conditions in LedaFlow are optional, and the reason for that is that if you don't specify anything, we've implemented a so-called gas-filled pipe option. So then LedaFlow just puts gas somewhere, which is a very convenient way of starting your simulation, because gas is the lightest possible production fluid, which makes it rather likely that it's possible to start production in your well or even in your flow line. So it's a very good default parameter for starting the simulation. But if you want something special, like in this case, we want to put drilling mud in the well, then we need, of course, need to specify volume fractions. And it's also possible to specify the pressure and temperature, but we'll not use that in the current demonstration. Okay, then we get to the demo. Yep, if I can just get LedaFlow back. So as mentioned, we're gonna create a well cleanup case from scratch. So in order to do that, I can first create a new case. So this is the case that I'm getting. I can show you what it looks like. So by default in LedaFlow, if you create a new case, then you end up with a single pipe, basically, with a flow boundary and a pressure boundary at the end. And then it's 300 meters of horizontal pipe. So the first thing we need to do in order to make this into a realistic well is to change the pipe profile, so it's no longer horizontal. So for that, we go to the pipe editor. Then over here, the profile that we're going to put in, we're going to change to TVD MD coordinates, which are custom for well definitions. So in this case, we're going to simulate a 2 kilometer vertical well. So for that, I'm putting the same TVD and MD coordinates like this. Then we can apply this. So it's perfectly vertical now. We need to put in some suitable ambient conditions. So we want to simulate a reasonable geothermal gradient. So I'll put 5 degrees at the wellhead, which is kind of similar to, let's say the temperature in around Norway in the sea. And let's put 70 degrees C for 2 kilometers downhole. So this is essentially the temperature of the reservoir. And we'll use a linear or a vertical interpolation. That's called Z interpolation in LedaFlow. So this gives us a linear vertical temperature gradient, basically, which is the most realistic for a well. Then we need to change the heat transfer characteristics. 1000 watt per square meter per Kelvin is kind of a lot. It's more representative of the kind of heat transfer you get if you have water flowing around a steel pipe. But in the kind of formation or rock that we're talking about, it's more reasonable to have a value of around 50 watt per square meter per Kelvin. So we can just apply these settings. Then the last thing we need to define for the pipe is the geometry. So this is where you would, for a flow line, you would normally define the wall definition here. But here, since this is a well, we can use the completion information and the well builder in order to generate this automatically for us. So if we go into the well builder, here is where we can add casing. So LedaFlow calls everything a casing, even if it's tubing. So we need to put in 2 of them in this case, if you want single annulus. So here we can see what happens. So there's a tubing now on the inside and the casing over here. Of course, we need to correct this a little bit. So the first casing, I'm putting this 1.5 kilometers deep, and then 2 kilometers for the other one. So the tubing is going a bit deeper than the other casing. Need to put in some reasonable diameter. So let's make this a 10-inch diameter, and a little bit bigger on the outside. And for this one, we put 6-inch with a reasonable steel thickness. So that defines the size of both the tubing as well as the casing. So that looks good now. And then in this case, we want to simulate a well cleanup, which means pushing out the drilling mud, both from the annulus and the tubing, using gas lift going through the annulus. So this annular space, which is highlighted in purple here now. So that one I have to change the material from cement to an annulus, and that way I can put fluid in it, and we simulate the flow in it. So the annulus here is kind of handled as a material in LedaFlow, and it knows how to create a pipe in the simulator. We also need to say how much cement we want on the outside of the pipes. It's not so important because the heat transfer is very similar to that of the formation rock typically. So let's just put 20 millimeters here. Now if we apply this to the pipe, then we can see here that this table has already been filled out by the well builder. So you can see that, okay, we get the diameter here, which is the inner diameter of the tubing, and also the wall definition has been set up in a proper way. So now we're all ready to get annulus. Now if you click OK, you can see that in the network viewer over here, the annulus appears, which is kind of like a pipe wrapped around the other pipe. So just for ease of understanding, I will rename this pipe to tubing. Let's call it tubing 1, so that is clear. So this is now the tubing, and this is the annulus around it. Okay, I forgot one small thing, and that is that we're still using the default mesh in LedaFlow, which is a bit coarse, so it's using around 30 cells. And then it's a good idea to remesh it a little bit. So we're using the default setting of 20 meter vertical cell size. Yep. So now we've remeshed it, and we can see that we're also capturing the start of the annulus more accurately now. So it starts exactly at 1.5 kilometers as intended. So that's good as well. Okay, now we need to add some more stuff to this model. So let's start with the case settings. So here we need to define, for instance, the PVT. So we can use black oil, which is very handy for well simulations. So we can use the default parameters, which include a GOR of 100 and a water cut of 10%, and then also some standard specific gravities. So that's okay. We don't need to change those for the demonstration. And we just need to associate it with the pipe so that LedaFlow knows what PVT to use. Okay, and then the second thing is we need to turn on custom fluid tracking so that we can have mud in the well. So we're using oil-based mud in this case, and by default it has a density of 820 kilos per cubic meter and a viscosity of 2 Pascal seconds. So that's okay for the demo too. So we're just using the default settings there. Okay, those were the case settings. So I just need to change one more thing in the numerical parameters. So I'm going to lower the CFL a little bit, and also the maximum time step to make it run a little bit slower, because actually the cleanup that I'm doing is going to be quite violent. So there's a lot going on there when we're cleaning up the well. So it's good to run it a little bit slower time step. That's okay. Now we need to add some equipment to the pipe. So right now we only have the bare tubing and annulus, but you also want to have some reservoir production, of course. So I can do that by adding a well device to the tubing. So it looks like this. So we need to verify the position. So it's all the way at the bottom of the well, which is okay here. So I'll just add some parameters that I've figured out before. So we're using the same temperature as for the geothermal gradients, so 70 degrees at the bottom, and a reservoir pressure of 235 bar. Default PI and injectivity values, they are reasonable, so I will leave those. So that is okay now, so we can use this. And then the second thing I need to do is put in a leak for the gas lift valve. So we're going to put it all the way at the bottom of the tubing. So yeah, if you do any other simulation, it's possible to put it at any height, and also to add more than one gas lift valve in LedaFlow, so you can have multiple, and you can see them opening and closing during the simulation then. But here we're just going to use a single one, and it's modeled as an orifice, so we're not using the gas lift valve tables here either. Okay, that's the gas lift valve. So that's all good right now. So then we need to change the outlet nodes. So this one, it's the wellhead, so I'll just rename it, just so it's clear later when we're going to look at the results. This one is configured at 80 bar by default, which is okay. And the other node over here, this is where the gas lift is coming from, so I'm just going to give it a suitable name. Let's call it gas lift. And then this one, we need to increase the pressure a lot if we want to clean up the well, because the hydrostatic pressure or the hydrostatic head of gas is much lower than the liquids that we're displacing. So that means we actually need to ramp up the gas lift pressure quite a bit in order to get this to work. So we're going to increase it during the course of 10 hours from 80 to 200 bar. So we're just linearly ramping up the gas lift basically. So that's okay like this. And let's see if there's any warnings and errors. We can see here that, okay, LedaFlow didn't really like the fact that I still have an active flow boundary and PI well. So this is just a reminder that I forgot to turn off the flow boundary over here. So that, of course, I need to set this flow to 0 because we're now using the well device and not the flow boundary for inflow. So that's okay. And then the other warning that we're getting is that it likes to have an initial flow rate estimate. Even though we're not going to use this in this case, I'm just going to put a value here. So we're not going to do a steady state initialization, but I'm just putting a value here so that I can get rid of all the warnings here. So now we know it's set up properly. And then there's one more thing I need to do, and that is to get drilling mud in the pipes. So I'm going to use the initial conditions for that. So I want to have oil-based mud in the entire tubing, basically. So the oil-based mud, it's 100% pure. So this custom fluid fraction, it's basically it's useful when your custom fluid is not completely pure. Like for instance, if you have glycol that can be mixed with water, then it's possible to put this at like 90% or something like that. But in this case, for oil-based mud, it's always 100%. And then this oil-based mud, it's in the oil phase, so we need to make this 100% oil as well. So now I have filled my tubing with oil, and the oil consists of 100% oil-based mud. And that's how this should be read. So I need to copy this definition because we need to repeat this for the annulus as well. So if we go to the initial conditions there too, I want to specify the volume fractions. We just copy the same thing in here, all the way from the bottom to the top of the annulus. And now we can run this case. So just we're initializing with the user-defined initial conditions, and we're running the dynamic calculation afterwards. And I want to run it a little bit longer than the time it takes to ramp up the gas lift, so I'm running for 12 hours. Okay, we can see that the case is initializing. So that was already the initialization done. And now it's running the dynamic simulation. So this takes a little bit of time for 12 hours of simulation, but in the meantime, I can already create some of the plots that I would like to use. So we're not wasting any time. So I'm going to make some trend plots in order to study how good the cleanup is. So first of all, I want to plot how much of the drilling mud is left in the case. So I can do that by plotting for the annulus and the tubing. I can plot the custom fluid total mass, which gives me an indication of how much drilling mud is there in the annulus and the tubing. So I'm just going to plot this. Here we go. Secondly, I want to have a look at what happens at the gas lift valve. So I can plot some mass flow rates at the gas lift valve. So I can plot the total gas and the total oil mass flow rate through the gas lift valve. So I can distinguish between the gas lift, which will show up as gas, and also I can I can also plot the oil curve over here, which will give me an indication of how much oil-based mud is coming through. So let's just plot that. And then finally, I can have a look at the well device, which will tell me something about if we're injecting or producing and how much. So let me just plot the total mass flow rate there. That will give me an indication of when the production starts. Okay, and then I can turn on the auto refresh in LedaFlow, so then it will automatically update these curves when the results come in. So we can just basically lean back and see what is going on. We can already see that something interesting is going on. So if you look at the first curve over here, which is the oil-based mud total mass in the annulus, we can see that this basically it goes down, and it's increasing the rate at which it's being displaced. And then that is because we're ramping up the pressure at for the gas lift. So we are basically displacing this, displacing the oil-based mud at an ever-increasing rate. That's why it's looking kind of like an inverted parabola. If I just change the unit on this axis, it's a little bit easier to understand. Otherwise, we have all these big numbers. So you can see here that the annulus has been cleaned up after approximately 7 hours of simulation. So it takes 7 hours to get rid of all the drilling mud from the annulus. And then afterwards, we can see that cleaning up the oil-based mud from the tubing is actually very fast. So then it takes only 1 more hour in order to clean up the tubing. So really the delay is because we need to clean up the annulus first, and then very quickly we can push out all of the mud from the tubing, basically. The reason for that is that at this point, when the annulus has been cleared of drilling mud, that is when the gas lift starts to come through the gas lift valve. So we're immediately pushing gas lift quite deep in the well, and that it's very quick to push out all the to push out a lot of the oil-based mud from the well then. Plus it also has the benefit of getting a nice push from the reservoir. So it's very easy to get it started then, basically. Now you can see here that so we're already producing as soon as we get a little bit of gas lift. That's because the weight of the drilling mud is kind of balanced with the reservoir. So we just need a small push in order to start producing. And then at the end of the simulation, we reach a stable plateau. This is basically our steady state production. So this is just showing that, okay, the well cleanup is successful. There's no drilling mud left in either the annulus or the tubing. And then we reach a steady state production, which is nice and stable. And probably we could reduce the gas lift after the cleanup operation. Probably this well doesn't need any gas lift in order to produce, only for the cleanup. Okay, I think that's all I wanted to say. And we can go to some questions, perhaps.
Yeah, thank you. Thank you for that, Wouter. We don't have any questions just yet, so if you'd like to type one in, please go to the questions drop down. There's a separate pane on the right-hand side you should see. And please just, if you type a question into that, we can then reply. Okay, Joshua sent one in. Why is oil non-zero in the leak? Is there enough information for you, Wouter? Or?
Why is oil non-zero in the leak? I guess what he means is why there's oil going through the leak, and that is because we're cleaning up the annulus by pushing gas lift from the top. So basically, we're pushing all the drilling mud through the leak. So we're kind of using this gas lift valve as we're essentially using it as an offloading valve. So we're pushing all of this drilling mud that we have here. All of this gets pushed through the leak as oil here, and then after it's gone, then we're taking over with gas. So it's actually not unusual for oil to go through a gas lift valve if you're doing a cleanup operation.
Yeah, okay. Josh says, no, okay, oil is oil-based mud, so that's okay.
It's showing as oil in this curve.
Yeah, yeah. Okay, that's good. Any other questions anyone would like to ask? Oh, hang on, there's another something popping up here. Okay. That was Niraj, that's okay. Okay, well, we don't have any more questions, so what we'll do is we'll sort of conclude the webinar. Thank you again, Wouter, and thanks for everyone who attended. You'll get a follow-up email within 1 day with a link to view a recording of the webinar. And if you have any questions after watching the recording or just after today, please send me an email and we'll get in touch. On behalf of Kongsberg, thanks for joining the webinar, and we hope to see you at the next one. Enjoy the rest of your day. Goodbye.